So I'm going to go ahead now and work through some problems that are taken out of chapter 9 in the book. These problems have to do with stability and equilibrium. And, in general, equilibrium is that condition where you have that the sum of the forces around on an object is zero, around a center of mass or center of gravity is zero, and then you also have the sum of the torques around that center of mass is zero. Doesn't mean the object is stationary, right? Could still be moving and be in equilibrium, but in general, we're probably going to be dealing with stationary situations. So we have this situation here, right, where they give us this. This is figure 949. Chapter 4 is one of your assigned homework problems, but this is chapter 5. Sorry, number 4. But here we have number 5, and this relates to the same figure. So here it says, okay, it wants you to calculate the forces Fa and Fb that support that the supports. So there's a support here, and there's a support right here. Exert on the diving board, and you have this 52 kilogram diver on the end of it. And they tell you to ignore the weight of the board. So the board is, we're going to assume, for part A at least, is negligible. It's not very strong. Or basically it's, make believe it's massless, which is not true, but whatever. And then part B will actually take it into account. So let's start with part A, right? So we're going to ignore so we can sort of draw this thing out, right? And we can kind of just draw it out as a, let me do it this way. Insert this picture here and sort of kind of do a free body diagram, I guess. So like this is the diving board. And what I'm going to do is I'm going to replace the woman who's standing here just by a mass. And that's her. So she's going to be mass M, and she's like right at the edge. So we'll just put that mass right there, M. And we can kind of create a coordinate axis. And what we'll do is on an XY axis, right? So you can put the origin wherever you want. So it doesn't really matter. I'm going to put the origin here. So I'm going to say that so if we kind of do the x-axis here, and that's the y-axis, we'll just call this point here, this is the origin here, 0. 0. Okay. So again, part A. Okay, so for part A, right, we just want to know what are the forces. So obviously there's a force going up here, Fa, right, because the diving board is pushing down, right, and so there's going to be an upward force there. So there's Fa pointing up like that, right, and then we have Fb, maybe say over here, also pointing up. So these are the forces that the two supports are exerting. So that's Fb, like that. This, and if we were to give this a coordinate, right, this is going to be 1, 0. And the girl here, right, the diver, I'll make her mass green. Right there. Make her, let me erase that. So everything's getting pretty messy. Make her green. Her mass, her weight is going down like that, mg. And her coordinate point is 4, 0. Okay, and so this is the situation that we have here. And we can measure these, you can measure these from any point that you want, right? That's the beauty. So let's do the equilibrium condition, right? So first of all, for equilibrium, we have two conditions, right? So equilibrium, static equilibrium here. The first condition is that the sum of the forces equals 0. And that's not too bad, right? Because if we look at this here, we have Fa points up, Fb points up, and Mg points down. So we can write out this equation, right? Fa plus Fb minus Mg equal to 0. And that's an equation, right? We could simplify it a little more, but I guess I'll just leave it like that and call that equation 1. The other one is that the sum of the torques is equal to 0, right? This thing is not rotating around any particular axis. And, we can place the axis, we can really place the rotation axis wherever we want. Typically, you would place it at the center of mass, but it doesn't really matter. So what I'm going to do is let's just place it here. Let's place it at the origin, right? And so remember torque, right? That's Rf sine of the angle between them. But in this case, the angles are each 90 degrees, right? That's a 90-degree angle. That's a 90-degree angle. And that's a 90-degree angle. And the sine of 90 is 1, so we can kind of just ignore the sine piece here. So it's basically a force times a distance, right? We'll pick this as our pivot. Doesn't matter what you pick. So so it's going to be, and again, so for torques, because you're sort of using the unit circle convention, counterclockwise is positive and clockwise is negative. Oops. So we're, the idea is that she would be trying to pull, this thing would be trying to go clockwise. So we're going to be dealing with negative torques. It won't matter in the end, you'll see. But the bottom line is, okay, so we have minus FA, right, times 0, because it's 0 meters from the pivot, minus FB times 1 meter, plus, sorry, those are positive. Sorry, because those want to go, hold on one sec. That one's going up, that one's going negative, and then this one, they would all be positive. Sorry. They all want to go counterclockwise, right? So they're all negative, which means that you could treat them as all positive, I guess. So let's just do it that way. Make them all positive. That we're basically, because they're all trying to rotate it in the same direction clockwise. So again, right, we have FA times 0 meters plus FB times 1 meter plus, and it's going to be 4 meters, right? So it's going to be 4 mg equals 0. Now, this obviously is 0 because that's just that. Anything times 0 is 0. Anything times 1 is just itself, right? So we have that FB plus 4 mg equals 0. So we can solve for FB, right? We can say that FB, right, this will be, I guess, equation 2. But if you solve for equation 2, you're going to get that FB is minus 4 mg. And then we can place that or plug that in there. So if we do that, what we're going to get is that FA minus 4 mg minus mg all equal to 0. And so we can solve, this is minus 5 mg, right? So FA minus 5 mg equals 0. And so we can solve for the force A. That's just 5 times the diver's weight, 5 mg. And let's just go ahead and plug in what we got. So 5, her mass, I believe they said, was 52 kilograms. There we go. 52 kilograms times 9.8 meters per second squared. So let's see what we come up with here. So 5 times 52 times 9.8 is 2548. So the force of A, 2,548 newtons of force. Okay. Obviously, we can get FB because we know that it's negative 4 mg, right? So FB, and these are really just magnitudes, right? The sign doesn't matter so much, ultimately. So if we do that, that's just going to be 4 times her weight. So 4 times 52 kilograms times 9.8 meters per second squared. And so that'll be, let's see, so 4 times 52 times 9.8, and that'll be 2038 newtons. Okay. Cool. And now finally, I think that's all they wanted was FA and FB. Okay. And FA is bigger, that makes sense, because it's, well, leave it at that. So, okay. Now we want to take into account the board's mass, right? So now the board has a mass of 28 kilograms, and we're going to assume that its center of mass is right at its center. So we're going to add a new piece here, right? So what I'm going to do is erase this here, right? Just erase these things, but we're still going to keep the sum of the torques and the sum of the forces equal to 0, and everything else is the same. So just bear with me for a sec. Erase all this stuff. Erase this. Get rid of this. And get rid of this stuff here. See you later. Alrighty. So now let's get back and do this one. So now we have this new mass, big M, and that's dead center. Right, so there's another big mg. And so the sum of the forces here, right now what this is going to look like is FA plus FB minus little mg minus big mg equal to 0. Okay. And now, and then we could do the sum of the torques. We could place the pivot, again, doesn't matter where you put it, but in general, if this thing were to rotate, it would like to rotate around its center of gravity. So we could put the pivot there, in which case this torque wouldn't matter, or we could keep the pivot here, in which case this torque wouldn't matter. Let's just put the pivot here, right? We'll put the pivot there. So the sum of the torques, again, they're all going to be negative or positive. They're all going to have the same sign. It doesn't matter what it is, because they're all the same sign. This is going to be, okay, so FA is now going to be, now this is dead center, right? So this coordinate, just to be clear, this whole thing is 2, 0, because it's dead center and the whole length is 4. So it's going to be FA, right? So FA times 2 meters plus FB times 1 meter. This one is times 0, so it doesn't matter, right? I'll write it out anyway. Mg times 0 meters plus little mg times 2 meters equals 0, because this is 2 meters from the pivot. Remember, you're measuring everything from the pivot. This is gone because it's times 0, and so what you end up with is 2FA plus FB, sorry, I'm leaving my vector symbols out there, this doesn't matter, plus 2GM equal to 0. Okay. And then this is going to be a substitution ultimately, right? It's going to be some sort of, substitution. I guess let's solve for FB, right? So if I do FB here, it's going to be minus 2mg, sorry, I wrote this GM, I should really leave it as mg, 2mg minus 2fa. And then I'm going to take this and plug it in there. So we're going to get Fa minus 2mg minus 2fa minus mg minus big mg equal to 0. Now the only unknown is Fa. So these are like terms and these are like terms, so I can combine those, right? So what I'm going to get is negative Fa minus 3mg, little m, minus big mg equal to 0. And I can just bring the Fa over to the right and solve for Fa. So Fa, in this particular case, is going to be minus, again, the magnet, this is giving a direction, the magnitudes are really what matters, minus 3mg minus big mg, right? You can even factor out the g if you want to be, this is left over from before. You can even factor out this g if you were so inclined. So let's do that, factor out the g, so Fa, excuse me, is g, right? And then in here we'll have a negative 3m, little m, minus big M. And we have numbers for all these, so now we can plug it in. So this is going to be 9.8 meters per second squared. And then in here, it's negative 3 times, she's 52 kilograms, and the diving board is 28. So she's 52 kilograms, minus the diving board, sorry, I left 38, but minus 38 kilograms. Okay. So just bear with me here. I'm going to do that. 9.8 times that. 3 times 52. Minus, plus 30. Or minus 38. We end up getting about 1901. Negative. But again, the sign doesn't matter so much. It's really the magnitude that matters here. And now we can get FB. And then, so basically you just plug it back in and get the rest. I'm going to move on to the next one, but then you would just substitute back in to get FB. You could plug it into this one to get FB, because now we have a number for this, and we know this. So that's how you get those. Okay, so let's move on to the next one that I have here. So here, excuse me, I have allergies bothering me a little bit. So here we have a traffic light that hangs from a pole, and you sort of see that going on here. what we have here is the uniform pole is this long. It's 7.2 meters long and has a mass of 12 kilograms. The mass of the traffic light is this. And they want to know the tension in this cable here and the vertical and the horizontal components exerted by the pivot A on the aluminum pole. Okay, so this is a more complicated problem. Let me make this a little bigger. Spend a few minutes on this. Hold on, draw. It's a little bigger. There we go. So the picture is like this. I'm going to call which one is the bigger mass? The traffic light is this, and the pole. So the pole is a smaller mass. That's going to be little m. So we'll put that there. That's right in the middle because it's uniform. Right. So if they say it's uniform, it's in the middle. Oops, sorry, that's not a good line. That's a really bad line. That's mg. Here we have big mg going down like that. There's a tension, so this thing wants to go to the right, so there's a tension pulling it to the left, holding it sort of in there, like that. There's Ft going, or I'll just call it big T. I know sometimes they use big T for period, but we'll just use it for tension here. So we got the period going back that way. Okay, we got these two going down. Yeah. And then there's going to be a force here, right? So there's going to be a normal force, essentially a reaction force at A, because what's happening is that there's going to be, this thing is going, they want, hold on, the vertical and the horizontal components on the pivot. Okay. So this thing is like digging in, sort of like pushing into the wall like that. You can't really see that, I guess. Right, it's kind of like pushing into the wall like that, and the wall's going to push back with a reaction force as a result, right? So we don't know exactly what that's going to look like. I'm not sure that it's going to be equal and opposite, right? But let's just say, let's place that, let's place it like this, I guess. Say it's like that. Sort of pushing back like that. Fn, we'll call that the normal force. Pushing back as this thing gets, well, it's not really a normal force, right? The normal force has to be perpendicular to the surface, right? So the normal force is really like this. That's what makes it normal, right? There's a normal force going back like this, and there's also there's going to be, well, there's two pieces here, right? There's like that and like that, because there has to be also going along like this, right? So that's sort of the picture that I want to go for here. So we'll call this FA, is this diagonal one. Yeah, okay. And this would be, so FN is FAX, and then this piece up here is FAY, like that. Let's do it like that. Okay, so we're in equilibrium. Sum of the forces equals 0. Okay, so what are the forces? Well, we can look at both the x and the y direction, right? In the x direction, or let's say the x direction. We know that the tension is going to the left, and this normal force, right, FAX, is going to the right. So I could write something like this, right? FAX minus the tension equals 0. And then in the y direction, like this, what we have is these two are going down, and then we have FAY going up. So we have FAY minus little mg minus big mg equal to 0. Okay, so those are two equations right there. Let me make this a little bigger. There we go. Okay. These are both unknown. Sorry, okay. These are both unknown. Don't know. I don't know that one either. I do know the two masses, right? So I can immediately solve for FAY. I can say that my FAY, right, that's going to be the sum of these weights. So that's going to be, little m plus big M times G. So let's go ahead and at least get the Y component of that. So the masses are 21.5 and 12. So that's going to be 33.5 kilograms. times 9.8 meters per second squared. So 33.5 times, times 9.8. So about 328 newtons. All right. Okay, so that gives us part of it, right? I mean, we're sort of getting there slowly. But we still have, part A really wants the tension. I mean, I couldn't say I'm solving this in any particular fashion or any particular order. I'm just knowing, anyway, so that's that. Okay. So, let's keep going here. Let's do the sum of the torques equal to 0 now. So the sum of the torques equals 0. So the pivot, well, obviously we can treat this as the pivot. That probably makes the most sense, I would say. So if we treat that as the pivot, these angles actually become somewhat important, right? Because it's going to be this, well, I'll sort of explain where this is going, right? So there are three torques, right? Basically, the blue vector, the red vector wants to rotate it, and also the tension wants to rotate it, right? So the way this would work, let me call this, we can label these. I'm going to call this, let me call this L, right? So this is going to be L, and this is also going to be L. This is the same lengths, right? Because we know that that it's dead center, right? So we know this is equally split. So the sum of the torques, we'll call, this is counterclockwise. The tension is a counterclockwise torque, so that's positive, and then these two weights are negative torques. So we're going to have, so bear with me here, right? So this is where it gets a little tricky. Not that tricky, but it gets a little interesting. And I'm going to call those L, and I'm going to call this distance here R. That's like this distance. So we have this triangle. I'll get into that in a second. So we're going to have RT, right, because it's distance times force, times the angle between them. So the angle between them is 37 degrees, right? So times sine of 37 degrees minus, so this torque is MGL, right? And the angle, if I sort of like think of it this way, right? This is the angle that we're looking at here. And that angle is going to be 90 minus 37, which is 53. So the sine of 53 degrees. And then the same thing, it's going to be the same angle here, but now it's going to be 2L, right? The distance is 2L. So it's going to be minus 2 MGL. Sorry, it's a big M. So let me be more specific. It's going to be mg times 2L times the sine of 53, all equal to 0. So keep that there separate. Okay, so we don't know L and we don't know R, but we can get them by looking at this triangle, right? So we have a triangle here that looks like this. So I'm just going to relabel this. This is L. This is 90, this is 37, right? I know this has to be 53 because they got to add to 180. And I know this is 3.8 meters. So I can get R and L just by using some trig, right? I can say here that the tangent of 37 degrees is opposite over adjacent. So that's 3.8 over R, right? So that R is 3.8 meters divided by the tangent of 37, like that. So let's see what we get. 3.8 divided by tan 37, 5 meters, or 5.04 meters. And then I can get L by doing, well, it doesn't really matter at this point. I can use any trig function. I don't know, let's use sine, right? Let's use sine of 53 now that we know R. We'll use sine of 37. Let's just use sine of 37. Sine of 37 degrees is opposite over hypotenuse, so that's 3.8 over L. So that L is 3.8 meters over the sine of 37. So let's see what I get. 3.8 divided by the sine of 37, about 6.3 meters. Okay. So now I can plug all these in here, right? I can go ahead and plug these things in here. So I have R is here. So actually, let me solve for t first, I guess, would be my goal. So if I go ahead and solve for t, if I do the algebra, and you should sort of do this on your own, just to verify that, in fact, it's true, and I clean this thing up as nicely as I possibly can, what I would get is something that looks like this. So it would look like GL. Again, I'm just doing the algebra. You could just put numbers in this thing at this time, at this point. But I like to do the algebra. So actually, there'd be a sine 53 out here. Sine 53. And then on the inside here, right, we would have little m plus 2m, like that. So that's that. All divided by r. So I did the algebra. But again, you can just plug numbers in. But, let's do it. Let's see what we got, right? So that's going to be 9.8 meters per second squared. Actually, you can already see I'm going to run out of room. So let me bring this down below it. Okay, so this is going to be equal to 9.8 meters per second squared in there. L, we said, is 6.3 meters. Then we have these masses, right? And I've already forgotten what they were. 21.5 and 12 for the big one. The small one is aluminum pole AB. Oh, they give us the length. So how did I get the wrong answer? They say AB. That's that. Let me just see this. 7.2 meters long. So how did I get my wrong L here? That's concerning. Because this should have given me the right answer. 3.8. Let me just double check that. So the sine of 37 is opposite over hypotenuse, yeah. Did I screw something up here? Let me see. 6.3. Sorry about that. They tell us AB. Where did I go wrong here? Because I should have gotten 7.2. I didn't need to go to all that trouble. But the trig should have worked. So let's see, 7.2 times the sine of 37. It's 4.3. I actually think this is wrong, this 7.2 meters. It could be a mistake. Because based on what they're saying, so the sine, yeah, that doesn't make sense. It doesn't give me 3.8 meters here. That's 7.2. Yeah, I'm going to go with my numbers. I don't know about this 7.2 meters. It's not making sense. Excuse me. Based on the trigonometry, I'll double check that, but let's just pretend that my L is correct. Because I don't see where my logic went wrong. I'd have to go back and check it out. All right, so it's, anyway, the small mass is 12 and the other one is 21.5. So this is 12 kilograms plus 2 times 21.5 kilograms. And again, assuming my, R and everything is correct here, which I do think it is, but again, I'll go back and check. That's 5.04 meters. So I'm going to plug those numbers in here and see what we get here. So 9.8 times 6.3 times this mass thing, so 12 plus 43, and then divide that by 5.04, and we get a grand total of about 674 newtons. Okay, so that's my tension. And now that I have my tension, I can go back to this equation, right? Because my FAX has to be equal to my tension. So my FAX is equal to my tension, which is 674 newtons. So now I have FAY and I have FAX, right? So FAY equals, what did we say it was? 328 newtons. And then FAX is 674 newtons. There we go. I'm still kind of bothered by this. So the sine is 3.8. Yeah, it's weird. Don't really entirely see what's going on there. I have to check this, but I'm pretty. The 7.2 meters is bothering me. The aluminum pole doesn't make sense. Anyway, sorry for that sort of. Yeah, that's point A, right? Yeah, 7.2. It's weird. All right, I'll check it out. But anyway, that's the logic, and I'm pretty confident in my numbers there. So anyway, hope you found this useful, and be on the lookout for some more of these.